Okay, I'm in this video going to do a complete, comprehensive calculation with no details left um, undiscussed for a definite integral using residue theory. Okay, this is a definite integral which you could have in principle seen in like a second semester calculus class, but you would have been hard pressed to be able to solve it. What integral? The integral from 0 to infinity of cosine mx divided by 1 plus x to the fourth power. Okay, so x is running from 0 to infinity, and this is the thing here. Now, I'm going to make an assumption to make my life easier that m is positive. You can include the m equal to m negative case and think about m generally in this, but I'm not going to, because it's going to make calculations downstream a little bit easier, I think. And furthermore, I think if we did want to make m fully general, we would have to have a lot of messy absolute value bars and things like that. So I'd just rather not right now and let you think about that. Because notice, right, the integrand is an even function in m, right? If you think about that function, that integrand as being a function of m, it's even in m. So there's some symmetry there that you can exploit if you really feel like it. Now, what I'm going to do, as usual, to bring the residue theorem machine to this integral is define a complex valued function which is closely related to the integrand here. Now, in other examples, we very straightforwardly just replace the real variable with a complex variable. We replace x by z symbolically, and that often works. But I'm going to do something a little bit different here. I'm going to define f of z to be cosine, no, the whole point, e to the I mz divided by 1 plus z to the fourth. Okay? Now, you'll agree, this is what's called a meromorphic function. And recall what that means. That means that it's holomorphic except for isolated singularities, which are poles of finite order. Holomorphic except at poles is what I'll say. Morphic on C except at poles. Right? There are 4 poles, and there are simple poles. Now, why this function and not just the straightforward swapping out of x with complex z? Why are we doing it this way? Well, the observation that I want you to make is that notice that if z happened to be real, if z is x plus 0 y, so that z is real, z is on the real axis, I'll say. Right? Then the real part of f of z, the real part of e to the I mz, in fact, I'll write it as e to the I mx divided by 1 plus x to the fourth. So obviously the denominator is already real. It's the numerator that's a sort of a non-real complex number potentially. And that ends up, but we can discern what the real and imaginary parts are using Euler's identity. So that's going to be the real part of cosine mx plus I sine mx divided by 1 plus x to the fourth, which is exactly, oh, this is getting a little bit unwieldy, which is exactly cosine mx divided by 1 plus x to the fourth. Does that make sense? You can't answer. But yeah. Okay, good. Oh, right. And that observation is crucial because when we go to actually write down this integral, okay, we will examine only the real part of it. Hopefully you know what I'm saying. Anyway, you'll see how this comes into play in what we're about to do. Okay. All right. So good. Now what do I want to say next? Maybe what I want to do now is lay out the contour that I'm going to integrate over, because of course we need a closed contour to employ the residue theorem to get some kind of handle on this function and its integrals. So if I draw for you a complex plane like this and like this, we know, and I won't justify this right now, that the singularities for this function lie on the vertices of a square. They're the fourth roots of -1, right? That's what makes the denominator there 0. And this is, I said I would do every detail, but I expect you to understand this at this point in your life. That upper right one in particular is e to the I pi over 4. Maybe I'll write that. And all 4 of these vertices of this square lie on the unit circle. Here's the contour I'm going to take. I'm going to start at the origin and go out along the real axis to here. Let's see, 1, 2, 3, 4, 5, 6, 7. And then I'm going to do a counterclockwise quarter circle. No, stop. I want to do a counterclockwise quarter circle like this to there, and then go down along the imaginary axis. Oh my God, this is a beautiful picture. I'm going to call this gamma. The whole thing is gamma. It's a piecewise smooth curve. There are 3 pieces. Okay. And I should say, this goes out to the point R. And therefore, this point up here is I times R, right? It's a quarter circle. And I'm going to call the 3 pieces piece 1, piece 2, and piece 3. Okay? I have 3 pieces, and I want to denote them because, of course, obviously, the integral over gamma of my f of z is equal to the sum of dz is equal to the sum of the integrals over each of these 3 pieces. And I want to make comments about these pieces. All right. First comment. The way we're going to kill that left-hand side there is with the residue theory. We're going to bring residues to bear on that. Okay. But what I want to say also is that integral on the right, because it only contains at most one singularity, as we let r grow, okay, the value of this integral will not change after a bit as r goes to infinity. So this stays invariant, or stays the same as r goes to infinity. There is a small, if your pedantry meter is blowing up right now, I hear you, okay, because when r is small, the integral is 0, doesn't contain any singularity, and then it clicks past the singularity and all of a sudden takes on some non-zero value, and then it just stays the same. That's the point that I want to make, is that it stays the same after taking on that non-zero value. Okay, leave me alone. I understand this. I just don't want to write it all out. Leave me alone. The second point that I want to make, that middle integral, the integral over the arc, okay? My claim is that goes to 0 as r goes to infinity. And that I want to prove to you in gory detail, because you should see it. Now, here's what my intuition tells me, okay? My intuition is telling me that this f of z, look at it, okay? There's my f of z. That f of z is going to be bounded. Wait. Yes, it's going to be sorry, it's going to be bounded. My intuition is telling me that f of z is going to be bounded for points along this quarter circle arc here. Why? because I have a keen enough understanding. Well, first maybe the easy bit, because this thing here, okay, it's gonna look more or less like r to the fourth plus one in modulus. The modulus of that denominator is gonna look more or less like r to the fourth. Okay, that's the first point. Maybe the next point is that thing there, that stays bounded as z goes for z in the first quadrant. The way to see that is to realize, oh, well, wait a minute. If I go out along this real axis here, e to the imz, as z is real, it's periodic, right? It stays on the unit circle. So that's not blowing up to infinity. But then what happens as I go along the vertical axis here? Along the vertical axis here, those are numbers of the form I times y, where y is positive. Now shove iy in there. You get e to the negative my, negative my, negative my. That's bounded. That's an exponential decay. Yeah? And so that's my intuition. That intuition's, we need to, I want to crystallize that into an argument, okay? But that's the intuition. Let's actually do that. Let's crystallize it into an argument, shall we? So let's deal with this second integral, and we're going to claim that it goes to 0 as r goes to infinity. Okay? Proof. So we have a nice tool for estimating the modulus of a contour integral of f of z dz. The modulus of this is bounded above by the length of the curve. In this case, the curve is this curve 2 times the maximum value for z on this curve of the integrand, the modulus of the integrand. Okay? So it sure would be nice if we could figure out what that is. So first of all, the length of 2, we know what that is. It's a quarter circle of radius r. A full circle of radius r is 2 pi r. So a quarter circle is pi over 2 times r. And then what about this max? So that's the max for z on this quarter circle of course, e to the imz divided by 1 plus z to the fourth. And so I should figure out what's happening with this. Well, first point, maybe. First point. What can I say about the norm of e to the imz? Okay, so to compute this, we should use a fact, recall. And I'll put some recalling facts over here. Recall that z, if you want to compute the modulus of z squared, that's the product of z times z bar. Z times z bar ends up being a real number, and a positive real number. Not only that, it's exactly the norm of z, the modulus of z squared. Okay, so to compute this is equal to e to the imz times e to the imz with a big old bar over it. Now, this fact is equal to e to the imz times the e to the imz with the bar just over the imz bit. Why is that? Just think about the Taylor series of e to the imz, or sorry, in general. Maybe this is not a recall, but this may be a new fact that we haven't talked about. But if you want to take this thing, this is always true. And the way you should prove that red fact there is by using the Taylor series for e to the z. All right? So if you believe that, then, and you know that the complex conjugate of a product is the product of complex conjugates, then you know that this is equal to e to the imz times e to the conjugate of I. Conjugate of I is negative I. The conjugate of m is real, so it's its own conjugate, and the conjugate of z, which is z bar. Great. Now this is equal to, by rules of exponents, e to the I m z plus z minus z bar. Right. Oh, and one bookkeeping thing that I messed up on. This is, of course, the modulus of this squared. Don't sleep on that. Not that that's hugely important. Anyway, it matters. I'm sorry, it matters. What am I talking about? Now, assume that z is in the first quadrant, as it is if z is on this arc. Okay, so for z on the first quadrant, what we know is that z is equal to x plus iy, where x is positive and y is positive, right? So z bar is equal to x minus iy, right? So z minus z bar is equal to 2iy, right? So now shove this into what's above. So this goes here now. And what we come out with on the other end, oh no. What we come out with here is e to the im times 2iy. But the i's get married, and we get e to the negative 2my. Okay, there we go. We see the exponential decay happening as y gets larger. No matter where we are in that first quadrant. You feel what I'm saying? I mean, frankly, I don't even need z in the first quadrant. Z can be in the first or second quadrant. And as we let go further and further out, why do I feel uncomfortable? No, it's fine because periodicity is happening in the good. Yeah, right. And as sorry, words. The goes bounded. Sorry. It's Saturday, okay? Just leave me alone. There we go. It's less than 1. Because you understand, this is real, that's real. M is positive, Y is also positive. This is bounded above by 1. It's a decaying exponential. Okay, cool. So that's the first point. That's important for this maximum here. Now, what's going on with the other bit? Well, or how can we continue this argument now? So, maybe I'll do it like this. I need to give some kind of estimate on that bottom guy. So I want to think about 1 plus z to the 4th. Now, in modulus. Now, for z on this quarter circle arc, I'm thinking about the denominator now. Here I'm going to use something which I don't think I've proved to you. I feel a little bit guilty, so I'm going to prove it now because of that. I'm going to prove something called the reverse triangle inequality. And I get a little mixed up about this, so please check me. Reverse triangle inequality. So let me remind you of the triangle inequality. This one's you should know. Very important. This one says that the modulus of z plus w is equal to the modulus of z plus the modulus of w. Sorry, did I say equals? The whole point is that it's an inequality. It's less than or equal to the sum of the moduli. Okay? Now, I'm going to use that to prove to you another inequality called the reverse triangle inequality. And this comes from the following sort of idea. I can express the modulus of z. I think this is the way I want to do it, as the modulus of z plus no, it's the modulus of, oh, okay, here's how I'll do it. This is equal to z minus w plus w. Z is equal to z minus w plus w. It's the old subtract something and then immediately add it back in trick. Okay? Good. And now this is less than or equal to, by the good old triangle inequality, the modulus of z plus the modulus of w. What? Excuse me? No. It's equal to the modulus of z minus w plus the modulus of w. So what this shows is that the modulus of z minus the modulus of w, I'm just subtracting from both sides, is less than or equal to the modulus of z minus w. Okay? Now, you should understand that the modulus of z minus w is equal to the modulus of w minus z. So you could run this whole argument again and conclude also that the reverse holds. So then we get the reverse triangle inequality, which I'm going to enshrine in the following way. That the difference in moduli is bounded above by the moduli of the difference. This is the reverse triangle inequality. Oh, and yeah, I should say, now swap z and w here. And then you'll come up with the reverse triangle inequality. Okay? So that, a little bit of an aside. Now let's go back to this blue thing here. And how are we going to use it? Well, I'm going to rewrite this as z to the fourth minus negative 1. Okay? I mean, that's obvious. That's just, again, a basic trick. I'm subtracting a negative, and that gives me a positive. But then by the reverse triangle inequality, this is greater than or equal to the modulus of z to the fourth minus the modulus of negative 1, which is equal to the modulus of z to the fourth, which is r to the fourth, minus 1 for r large enough. And we're going to take r to be large here. Okay? So that gives me a lower bound on the denominator. Great. So then we can look at what's happening way back at our inequality here. Wow. It's almost 25 minutes in. Okay, that's okay. That's okay. We're doing good. It's good to go into gory detail at least once, okay? So we're here. I'm going to replace this max thing. I'm going to come all the way down here. Oh, I should do this with a color. Let's go all the way down here. Even further. And say, okay, in green, this is equal to I'm having serious aesthetic issues today. Okay. Oh, Siri just activated. That's also pinging my. Okay. I want to sequester this, keep it in its own little box, because it's its own thing. Man, I'm insufferable. Okay, so we have here in green pi over 2 times r times, now, okay, the maximum. So first of all, that numerator is bounded above by 1. So this is the maximum value of 1, right? We proved that as in this discussion here, right? So the numerator is bounded above by 1. The denominator is bounded below by r to the fourth minus 1. So actually, I don't need this max anymore. These are bounds, so they hold for all z. 1 over r to the fourth minus 1. And for some reason, it decided to erase my line, and I got to put it back, because that's just the mood that I'm in. And that line is not going to work at all. Much better. Okay. Okay, so this is equal to pi over 2 times r over r to the fourth minus 1. And this goes to 0. As r goes to infinity. That's the point. Okay? What goes to 0 as r goes to infinity? The modulus of this integral, the integral over 2. Great. So this middle integral here is going to die. Excellent. Let's think about integral 3 for a second. So I want to think about the integral over curve 3. Remember, curve 3 is the one along the vertical, the imaginary axis of e to the I mz divided by 1 plus z to the fourth dz. What can we say about this integral now? Well, so we should parameterize that curve. We're going to think of it like, so for this curve 3, we're going to think of it as z being equal to I times y, where y is going to run from, is going to go from, goes from, so remember, we're starting way up high on the curve here. We're starting here and then going down to here. So we should start y at r, and then it goes to 0. So it's a little bit weird feeling, because y is decreasing, okay? But that's fine. And then what's dz? dz is I dy, right? Under this parameterization. So if I fill in the blanks here, what I get is this is equal to the integral from r to 0 of e to the I m times iy divided by 1 plus iy to the fourth power dy. Oh, no. Dz is 1 over I. This is crucial, actually. 1 over I dy. Yeah, this is very, very important. Because watch the magical thing that happens here. So I can pull the 1 over I out. And by the way, 1 over I is the same thing as negative I. That negative I can kill by flipping the sign of the bounds. So I'm just going to have an I outside. And then I'm going to have the integral from 0 to r. And now what's inside? What is the integrand? The integrand is e to the negative my divided by 1 plus, now what is y to the fourth? I to the fourth is 1, positive 1. So this is 1, this. Sorry, I'm getting excited. And the point is that this thing here is purely imaginary. There is no real part. Very important. This is purely imaginary. There's no real part of this complex number. And I could stress about what that imaginary part is, okay? But what I'm trying to get at is if you're looking at this integral here, and you know this part is purely imaginary, now this part is going to 0 as r goes to 0, then what you know is that this integral here is equal to the real part of this integral. Or no, I'm sorry. I said that wrong. Okay. And what you care about, of course, is the real part of this integral, because the real part of this integral is our given integral as r goes to infinity. But that's equal to the real part of this integral. So if I can write down the real part of this integral using residue calculus, then I win. Right? That's the crucial insight of this third integral being purely imaginary. Okay? This implies that the integral we want is the real part of the integral over gamma of e to the imz divided by 1 over 1 divided by 1 plus z to the fourth dz. Okay, now we undertake the residue calculation. Okay. Now we're going to do the residue calculation. So what I want is the residue of f at e to the I pi over 4, because that's this is the only residue that lives in the interior of this guy here. Now, I claim, and I'm right, that this is a simple pole. This is a simple pole. And the reason is because e to the I pi over 4 is a simple 0, is 0 of order 1 of the denominator 1 plus z to the fourth. Don't believe me? Take the derivative of 1 plus z to the fourth. That's 4z cubed, and that only has 1 0, and that's at 0. In particular, e to the I pi over 4 is not a 0. Okay? So it's a simple pole. So, yeah. So, first point, z equals e to the I pi over 4 is a simple pole. Second point, let's define f to be equal to g over h, where g is equal to e to the imz, and h is equal to 1 plus z to the fourth. Okay? Then what we can conclude is that this residue here, this is equal to g of z naught, so g of e to the I pi over 4 divided by h prime of e to the I pi over 4. So that's, and the derivative of h, I know you know, is 4z cubed. So that's 4 times e to the I 3 pi over 4. Okay? Now, okay, so all that's true. And what I need to concern myself with, okay, yeah, I, I'm going to find it profitable, I believe, to compute the real and imaginary bits of this crazy complex number here. Oof, this is going to be real interesting. Okay, here we go. So we're going to do some serious calculation. All right, okay, buckle up. So I'm going to shove e to the I power of 4 into g. So I get, now I'm going to start using inline notation. Is that okay with you? I'm going to write this as exp of imz. Can you deal with that? That just makes it so that I don't have to keep writing things in the superscript position. So the numerator is going to be exp of I times m times e to the I power over 4. This whole thing is going to get divided by 4 e to the I times 3 pi over 4. Okay. Really looking to understand the real and imaginary parts of this residue. E to the I power over 4, yeah, okay. We can write this as exp of im times, and real imaginary parts of e to the I power of 4 are obtainable using good old Euler's identity. So that's 1 over square root of 2 plus I times 1 over square root of 2. Right? Because the cosine, blah, blah, blah. Cosine of pi over 4 is 1 over root 2, and the sine is also 1 over root 2. And then this gets divided by 4 times I'm not sure if this is profitable or not, but I'm gonna use Euler's there. So I get now the cosine of 3 pi over 4 is, it's that one, which feels like negative 1 over root 2 plus I sine of 3 pi over 4, which is 1 over root 2. Yes. Okay. Okay. I think I'm doing this correctly. And then this becomes exp of, I'm going to distribute the im in, so I get m 1 over root 2, maybe I'll write it as m over root 2, minus m over root 2 this is times I, of course. This whole thing divided by, I'm going to factor out a 4 over root 2 times negative 1 plus I. Okay. This I'm going to simplify a little bit more. I think I want to do it this way. So this is exp of negative m over root 2. And then I'm looking at the numerator, and then I can rewrite that, the rest of it, in terms of Euler's formula. Cosine m over root 2 plus I sine m over root 2. So that's the numerator. The denominator I should be able to take care of. So 4 over root 2, I mean, that kind of simplifies the 1, 2, root 2 times 2. 2 root 2 times negative 1 plus I. Okay. And I should get that negative 1 plus I out of there by multiplying by the conjugate, right? That's the trick. And if I do that, so negative 1 plus I times negative 1 minus I think is 2. You can check that. Yeah, that looks right. So we get exp of negative m over root 2 and then so if that becomes a 2, then we get a 1 over 4 root 2. Does that sound, I don't know if I've done something weird there. There's the exp, and then I need to multiply this complex number by negative 1 minus I. And if I do that, oh boy, I get negative cosine m over root 2 minus I. Well, actually, I want to track the real parts first. So the other bit of the real part is going to come from I times negative I, which is plus, right? Is that a plus? I times I is negative 1, so then the negative, yes, plus sine of m over root 2. And then the imaginary bits, I actually don't even think I care about the imaginary bits, but I'll track them, is minus I cosine m over root 2, and then minus I sine m over root 2. Oh, no. This is actually the bit I care about, honestly, right? Because right. So this is my residue here, and it looks horrifying, okay? But now, okay, what I can do now is compute this integral. So the integral over gamma of e to the imz over 1 plus z to the 4th is equal to 2 pi I times this beautiful thing here. Do you believe it? So it's times all of this. Huh? What happened? Is it too big? There we go. Look at that. I'm good. Okay. Oh, and I should put big old bars around this. Okay, having fun yet? Okay, now. Okay, we can simplify this a little bit. This is equal to, the 2's kill each other, so we get 1 over 2 root 2 times pi. We have this exp here, so that's e to the negative m over root 2. All right. And then we have I times all this gross stuff Okay, that's good. And then the I and this minus i's that we see here and there, they get married and become a plus. Cosine m over root 2 plus sine of m over root 2. And what we know is that the integral that we wanted way at the beginning, where is it? This integral right here is the real part of this integral. So I swear we're almost done. The integral from 0 to infinity. Oh, and I need to take a limit as r goes to infinity. But oh no, I don't need to do that explicitly. Because the residue. Yeah. So of cosine mx divided by 1 plus x to the fourth dx. Well, that's the real part of this integral, because the real part of this integrand is exactly this integrand. And if you think about the way the sort of the contour integral sort of breaks down into its real and imaginary parts, it's the integral over the contour of the real part plus the integral over the contour of the imaginary part. Okay, so this is equal to the real part of everything above, all this stuff. Here, all of this. Duplicate, move it, and then resize it so it fits. Nice. But then what's the real part? Well, just look with your eyeballs. Everything inside that bracket is real except for this part right here. That's the imaginary part. So what we end up with is, in the end, pi over 2 times the square root of 2 times e to the negative m over 2 times cosine of m over the square root of 2 plus sine of m over the square root of 2. And that's it. That's the value of this integral. Okay? Wow. That was fun. It took us through quite a lot. And you can see here, a lot of it is about careful estimation. A lot of it, what we had to do is make sure that that second integral over that expanding quarter circle arc died. Yeah, let me actually, because I only have a couple more minutes here, let me just review the calculation we just did. So, in the gross, we have this integral here that we care about. M is positive. We define a meromorphic function, f, okay? And we define a contour which encloses one of the singularities, isolated singularities of this f, okay? The argument, the reason why we chose this meromorphic function is because the real part of that meromorphic function is exactly our integrand. All right? Now, in thinking about this integral over this contour, we broke it up into 3 chunks. What we know about this, the integral over gamma, is that it remains invariant as r gets large and larger and larger and larger. If r is large and r gets larger, the value of this integral does not change. It is equal to 2 pi I times the sum of the residue at this isolated singularity. Okay, cool. What can we say about this middle integral? Well, crucially, it goes to 0 as r goes to infinity. Why? Well, that was all of this work that we did here. That was this claim. Okay, the way that we did it, we made careful estimates of the numerator and of the denominator using well, our understanding of the exponential function as being bounded of e to the I mz with the I there. The exponential function e to the I mz being bounded in for the upper half plane, okay, and being and the denominator being bounded below by r to the fourth minus 1. The more heuristic argument is, of course, it's a polynomial, so it's going to grow like r to the fourth as we keep z on that circle. But to make that explicit, we use something called the reverse triangle inequality, which is very useful. Okay, and then we made the argument there. Crucially, this third integral, okay, along this arc right here, this arc of the curve, that third integral is purely imaginary. And what that means is that when we go to take the real part of the integral over the contour, that's not going to pick up any of this. That's going to get entirely ignored, right? And that leaves the fact that this this integral, the real part of it, is precisely going to be the real part of this integral, the real part of this integral by what we said here, because the integral, the integral over a contour of a complex integrand is the integral over the contour of the real part plus I times the integral over the contour of the imaginary part, right? So that's going to make it be the case that we can just take the real part of this integral here to compute the real part of that integral there, which is exactly this integral as we let r go to infinity. Okay? And that ends up with this formula, which holds for all positive m. Okay. That's more than enough. I feel as though I've fulfilled my promise. This was, depending on your proclivity, an enjoyable journey. Okay, so long.